here, right? Okay, folks, so we got a good one today, I think. Great debate. TRILL versus 802.1 AQ, shortest path bridging. Whoa, SPB. Sorry, guys. Sorry about that. What's this all about? So, TRILL, shortest path bridging, really talking about extending and enlarging layer 2 Ethernet networks. Ethernet has been growing in popularity because of its increased speed, its reduced cost, can get tons of different ways to plug in devices together. It's easy to use, pretty much plug and play, right? Well, as our networks are growing larger, we find that spanning tree just isn't quite cutting it. It's not getting us what we want. We want better multipath, we want better redundancy, we want better stability, less oopses. So there are two prevalent solutions that have been coming out. We got TRILL, it's been coming out of the IETF, stands for Transparent Interconnection of Lots of Links, and of course 802.1AQ, which is a designation given by the IEEE for shortest path bridging, and apologies again, gentlemen, for the SBP, it is SPB. I know, you can flog me later. So a couple things that both sides agree about here is that we need to build a larger layer 2. There's enough demand for it, and we need some sort of encapsulation to make sure that we have compatibility with legacy protocols, and just because that's what it's going to take to make this happen. There's unanimous agreement here that this new network needs to be controlled by some kind of link state distribution, and that's pretty much where we start to diverge. Now, how we're going to do that is up for debate. Let me introduce you to our speakers. So we have actually quite a well pedigreed group of folks here. We have folks with experience with patents, writing RFCs, protocol experience, writing protocols, and of course network operators. So we have Donald Eastlake over here, coming from Stellar Switches, who's also on the IETF TRILL working group. We have Peter from Huawei, Peter Ashwood-Smith, and Srikanth from Avaya, and Paul from Alcatel-Lucent, who are all active members of the 802.1AQ working group. The way we're going to run this here is we're going to give you some introductions to the actual protocols themselves. And I got it right this time. If you're interested in more in-depth coverage of the protocols, yesterday both sides gave a pretty good in-depth tutorials, about hour and a half long tutorials, so you can go ahead and load up the slides, or I don't know if the video's been archived yet. I think we got video on those. So you can find a lot of good in-depth information there. I'm going to give you just some basics just to give you the foundations for our conversations today. And then we're going to have a few minutes to contrast with the opposite solution. And I collected a bunch of debating points that I'll be bringing up as time allows, and then some open time for Q&A. So the SPB folks won the coin toss last night, so they're going to go ahead and do the initial intro, and then Donald will follow thereafter.
So this is shortest path bridging in 4 slides, so I apologize if it's a little quick, but like we said, there's a lot of tutorial material out there available for you. So what is 802.1AQ shortest path bridging? It is a collection of industry standards put together in a novel way. It consists of an industry standard, widely deployed, vendor-supported, test tool-supported Ethernet data planes, the 802.1AH and AD, so the MAC and MAC and the Q and Q data planes, combined with an industry standard, widely deployed Ethernet OANM test suite, so the 802.1AG and also the ITU 1731 suite of protocols. Combined, again, you're going to hear these words a lot, industry standard, widely deployed ISIS link state protocol, which we have only made very minor TLV extensions to. All right, so we're taking these 3 widely known industry standards and putting them together in a novel way. We're using these things to do inputs to calculations, to provide inputs to calculations, and those calculations allow us to provide shortest path routing, multiple equal cost shortest path routing, and not only for unicast but also for multicast traffic, essentially allowing us to create very large numbers of layer 2 VPNs on much larger scales with native Ethernet routing and native Ethernet data paths, native Ethernet OANM. Tens of thousands, like I said, of services are possible because of the 802.1AH ISID. So the data path has this ISID, so we're not bounded by that 4K VLAN limit. What's the statement? If a constant is not obviously too large, it's probably too small. So that applies in spades in this space. And we're building on top of tens of thousands of man-years of engineering effort at the IEEE and extending it slightly. Some of the applications of this protocol include very large layer 2s in the data center, so large layer 2 fabrics. I'll talk a little bit about that, but in support of the massive interest in virtualization and the cost savings that brings in data centers. Internet layer 2 exchanges is another area where this is very interesting technology. Metro Ethernet, a small Metro Ethernet or even a medium-sized one could be operated with this technology. Wireless backhaul as well. Anywhere where layer 2 VPN is important, this is an applicable technology. So just a quick look at how we support the wider scope of virtualization and better routing in a data center. 802.1aq allows us to put hundreds or even thousands of multi-terabit switches together. They can be put together with connectivity, which we call a fat tree. Essentially, it allows you to create a non-blocking connectivity between all of the different components within the switches within the data center. And that essentially allows you to have 100 or so terabit, or maybe even more, logical switch within your data center. This protocol is completely compatible with all the 802.1 data center protocols. In fact, it's being developed in the room next door to the 802.1 data center bridging folks. So we're working at the same conferences. Subnet virtualization is a major aspect here of the data center, and 802.1aq allows you to go to a single point within the network, make it a member of a subnet or a layer 2 VPN, and it automatically, the subnet extends to contain or to extend to include that new member. Also, members can be removed very easily and quickly by just simply a single point provisioning. As I mentioned, the Ethernet OANM is complete end-to-end Ethernet OANM here. And the data path MAC in MAC is absolutely ideally suited for a data center. The isolation is one of the main goals in a data center, and MAC does that for us today without any new data path work. So visually, just a quick slide to show you kind of what's going on here. Here's a 36-node network running ISIS on all of these network-to-network links. ISIS advertises the topology and the membership information. We then compute up to 16 shortest paths through this network, allowing us to have 16 equal cost multipaths. Not only do we allow the unicast traffic to flow on a shortest path, but we also allow the multicast traffic to flow on a shortest path. We only do learning at the edges, which is one of the goals of scaling, of course. And again, it's a MAC and MAC data path. So here visually is what's going on. I have my shortest path tree there shown in that pink color, which has been pre-computed by the protocol. Unknown unicast or multicast traffic arriving from an edge device is multicast using MAC and MAC encapsulation specifically only to the interested members of that layer 2 VPN. We learn at the edge the association between the incoming traffic, client address or the host MAC address, and the SPB device at the edge. And then, of course, a unicast packet can now flow back on the shortest path. And at that point, we've now learned the association in both directions, and unicast traffic can flow in both directions. Encapsulated MAC and MAC. The host address is encapsulated in just another layer of MAC. But as I pointed out, using that lovely big 24-bit ISID, getting us away from the 4K limitations of the current VLAN. So this is a slide I've shown a few times, and kind of like this one. It just shows the corridor of ECMP available to 802.1aq between a variety of different sources. So it's just circling around showing different sources and destinations. And that corridor is completely available to you for your traffic. One of the things that we do here is we assign the traffic to the path at the head end, so it's not being continuously reassigned as you go. We call that rifle forwarding. It's like aiming exactly where you want to send the packet and you shoot it through. And I'll use this in contrast later to a shotgun type of forwarding when we talk more about TRILL. So here's an example of that, the ECMP behavior in a 2-layer DC fabric. This is a 16-node spine and 32-node aggregation. And what we're seeing here in the upper right-hand picture, I don't know if my mouse will work here. Here it is, yeah. Here's the source and here's the destination for unicast, and we're seeing all 16 ECMP paths superimposed. They're all available to you. And here we're seeing one of the multicast trees, which is available for, for multicast, of course. And all 16 of the important point being that all 16 of those spine nodes are available as replication points. So we can support multicast, and we can also support multicast ECMP, and we can use each of those different 16 shortest path trees for multicast. So our multicast is not only congruent to the unicast, it's also shortest path. In terms of the ONM capabilities, I mentioned the fact that we are building on top of 802.1 AG. So the entire protocol suite, and Srikanth is going to talk a little bit more about this, but basically the continuity checks, the loopback, the trace routes, the discovery protocols, performance monitoring, all of that stuff is designed to work transparently to the protocol 802.1AQ, and in fact to work with the protocol. So there shouldn't be any surprises there. And as I said, thousands of man-years of effort have gone into this protocol suite. So I guess I'll turn it over to Srikanth, who's going to talk a little bit more about deployment experience and ONM.
Hi, I'm going to talk a little about deployment experience with SPB, with Mac and Mac data planes, and 802.1 AG, and how all three of them work together, and how each one of them does not invalidate the work that was done on the other standards, right? So I'll kind of look at some of the OEM capabilities here. What do service providers want to do? They want to run reachability tests in the network. Can they reach a foreign device? And here's a unicast reachability test. You're trying to do ping from this device to this device here, ESP, and saying, run a unicast test for me, right? So, and you can run this test with one ping, or you can run this test with 10 pings. Here's unicast trace route at running natively at layer 2. You got network. You got the shortest path highlighted in red here, right? The red links are the shortest path links. And what you're seeing here is from this switch, I want to find the path to this switch, and I want to do it in data path. I don't want to trust what my control plane is telling me, that what the path is, but I want to validate it for myself. 100% so goes the same fate sharing as what your data traffic does. And here's what you see. The output of this command here shows you're starting at EL2, you're going to EVS, which is one hop away, you're going to CS0, second hop, and finally the destination, the third hop, ESP, right? Well, SPB also does multicast trees. It can build very efficient multicast trees, and the customers want to know what my multicast tree looks like, and I want to see and trace, again, this multicast tree using the same exact forwarding records that I use for my data traffic. I don't want to trust my control plane. I want to verify where my traffic is going. Okay, here's the multicast tree for this node, EL2, that is built in red here, right? We're going to issue a command for a particular service instance that's using that multicast tree. In this case, it's ISIT 5010 is the number we've chosen. And issue a command here that shows layer 2 trace tree on algorithm number 10, ISIT 510, service instance 5010, right? Here's what you see. You see a fork at EL2, right? So this is corresponding to this fork here. Then you're going to see a fork at EVS, which is where the tiebreaker is taking it for this particular algorithm. And once it reaches CS0 and CS1, you have a single hop to the leaf node of the tree, ESS and ESP, right? So that's what you're seeing here. The next one, okay, I can see the multicast tree from the root of the tree, but I'm not at the root of the tree. I'm on this node here, and I want to trace the remaining portion of the tree. Okay. Here's what you got. You got a tree that completes the rest of the tree. EVS is the first hop for the second portion of the tree, and it just goes forward. Here's here's a multicast tree trace from the leaf node. You're logging on the leaf node and saying, can I look at the multicast tree? And it's saying you're the leaf node, there's no more tree left behind you, right? A little bit more about the experience on where shortest path bridging is. It's currently deployed in live networks, service provider, and enterprises. It's deployed in mesh topologies, it's deployed in ring topologies, it's deployed in hierarchical ring topologies, deployed in government networks. We have one municipal area network that we have deployed it in. It's providing residential aggregation services as well as business data services. And at the edge, it can support any kind of access network. It can support, it does not preclude you from using your proprietary access networks at the edge, or you could use spanning tree, or you could use proprietary ring technologies.
So I just got told I need to make this a little quick, which is good. I only have 4 slides, so I'll wrap it up with a summary as best I can. So to continue and basically highlight what both Peter and Shrikant said, shortest path bridging is well known in the industry for its IEEE basis. You know, we've been rather surprised about the interest we've seen out of data centers, in particular with the MAC and MAC encapsulation, because it allows the networks to scale to some extremely large size and allow that the switches in the network and the routers in the network don't ever have to really learn the server MACs, but yet we can support an exponential number of servers like than we could in the past. One thing actually I was going to try out here is that there's a lot more work going on than basic layer 2. And if you come from a routing background, you tend to think of Ethernet as simply something that connects your routers together. But these environments allow, especially in data centers or metros or residentials, to grow some pretty large layer 2 domains because Moore's law has been extremely kind to us. So it gets us to the point where the design of the SPB and the IEEE has been looking at this so that we can go from small layer 2 networks of 2 switches to 1,000 switches and scale in place with simply a software upgrade of the switches in place. It's using an existing Ethernet control plane, and it provides in the protocol ability not only to do just a LAN topology, but also a E-tree topology, a line topology. Now what gets interesting is because we're using ISIS and the basic construction of what we've done to the fibs of these switches, they're actually acting like MPLS. And it's no surprise considering that most people working on this in the IEEE, well, all of us actually happen to have a lot of the patents behind MPLS and VPLS and GMPLS. So from the very beginning, there's been a lot of thought about the operational models behind what these networks will look like. We have people from data centers, we have people from metros, we have people from residential environments, all looking at this, saying how do we scale this and how do we make it better? But we also look as we can do more because it's ISIS. We can actually provide IPVPNs on this. We're using a value called an ISID, which is basically, think of it like the next generation of a VLAN, but it gives you 16 million services instead of 4,000. And by the way, because of it's an ISID sitting there, it means that we can do 4,000 VLANs on any port attached to an ISID and rewrite the vid going in and out any port. So the whole VLAN scale issue, gone. But we can also do IP routing. And it built into it, because it's operating like MPLS, it natively extends an MPLS network. Right, so it really nicely plugs into a very large network. And in itself, especially when you think about it working with PBVPLS or the IPVPNs, it's a standard and native way that you could actually right now, today, in a lot of environments run this, extend a data center to data center connectivity so that 2 racks and 2 different data centers would think they're locally connected together using standard Ethernet forwarding back and forth. So it gets pretty nice if you think about all the deployment models that are available here. Now one thing that might not be clear is Peter talked about the rifle shot mentality. There's a lot of nice things you can actually derive out of that because of that rifle shot mentality. And you also notice I noticed at the top of this thing called SPB-M, because there's 2 modes to SPB. There's this V mode and M mode. V mode simply says it's standard Ethernet, standard VLAN control, and we can go with the 4,000 to 4,000 control inside the environment. So if you don't want to use PBB, don't use PBB, use regular Ethernet. If you want to use PBB because you're worried about the scale or you want to separate the server MACs from your actual switches, so if you look at this and you were to think of there's 2 switches on left and right, or excuse me, 2 servers, the switch in the middle, C, never sees any of the MACs from any of the servers or any of the PCs, none of it. It's completely hidden from the server's perspective. They can't hack into it, they can't see it, they can't do anything to it. What's also interesting is that because that ISID, that 201 for example, it provides a very interesting thing. It's what triggers the multicast state. And it's announced in ISIS like an IP route. And that's a very important thing to realize is that we didn't change anything in ISIS. because most of us have deployed ISIs. I myself have worked in some pretty large environments in both tier 1 carriers as well as enterprises that ran ISIs. We know how good it is. We know all of its warts and we know all of its benefits. We did not want to change the protocol, and we didn't. We simply just added a simple TLV that triggers an optimized Dijkstra that then gives us a shortest path multicast tree, and the unicast is just a subset of that. But the rifle shot provides another benefit. If you think about all the work we're doing also in IEEE on fiber channel of Ethernet, it provides a perfect environment for a deterministic path for fiber to Ethernet built in. Go back to also all the O&M that we have available to us in 802.1ag and Y17. We've brought forward all of the SONET O&M to Ethernet. And it's well deployed. We have networks running all over the world with it right now, which means that we also get a lot of the SONET O&M that we expected for fiber channel right on top of Ethernet, and it's already there and well deployed. Bugs are already nicely worked out. One other thing that's kind of interesting about this, that's hidden inside the draft, and most people don't really know it's there, is this ability to reuse this ISID. And if you remember, I said it automatically creates this multicast state in the background, and you can basically tell it to use a lot or use a little. But in particular, this one little benefit we have there is that we call it a default tree. It means is that we basically create a tree in a background that acts kind of like a bare channel for just these nodes. And what they do is they basically just join a tree and they sit there quietly. But it's used particularly just for link state updates. So the nodes just naturally will always do the standard hop by hop, share their link state advertisement to each other. That's not changed. This is an additive. So what happens if a link fails like between these two switches in the middle, it'll actually, these nodes will take their link state update and drop it on the tree, which means basically every single node that's participating in this network learns about that failure at nearly the same time and reconverges the network completely in one time. Most tests that we've seen that actually ran this thing were showing that we could actually converge a fairly large network of 100 switches or more in less than 30 milliseconds. It was very interesting to watch that because only the paths that were affected and only the services that were affected had to reroute. So to wrap up, one of the things you got to look at this is we see a lot of interest in this thing for a lot of paths. And you can see we're sharing a lot of paths here in their rifle shot. But that doesn't stop us from also doing a shotgun effect. So we can do both actually with SPB because we did it in more of an MPLS-like fashion. Very aware of what a service is, making VPNs kind of bringing them to Ethernet, right? So that when you configure an ISID, it is literally like a service, a VPN. Even though it's an ELAN, you can use it and think of it just as you would any other Ethernet switch out in the world today. And the design intent is that in 5 to 10 years, and you go to your favorite vendor to buy a switch, and you plug it in your network, it'll be running SPB by default instead of spanning tree. Because what it nicely does is it basically obsoletes MSTP, RSTP, MVRP, MMRP, and you just can keep going on that laundry list, all in one nice shot, one in nice protocol, just turn it on and it runs. But that's not the end of it. Because it's ISIS, we have all the things we have in MPLS aware to us, colored links, colored pools. We can just do a lot of the things we do in MPLS, and we can actually apply it to Ethernet in these paths too. So the one thing to realize too, if you hadn't caught on yet, all these switches are running without broadcast, not flooding learning. All of their fibs are explicitly controlled, right? But we still allow the flood and learn on top from the server, so there's no change in Ethernet. And because it's standard Ethernet control plane, it just works. Switches that have been around for 30 years just basically need a software update, and they switch natively on Ethernet. So, is that fast enough? Okay. All right. Thank you.
Hi there. I'm Donald Eastlake, co-chair of the IETF TRILL working group. I'd like to recommend that people do look at the tutorial material from yesterday. I gave much more there, and I'll only just be able to touch the surface here. And you're welcome to look at the shortest path bridging tutorial from yesterday also. So what is this TRILL thing? It's a new standard protocol. It does layer 2 bridging, but it really uses ISI's link state routing to accomplish that. It's a good trick. Invented by Radia Perlman, somebody you may have heard of. She invented spanning tree quite a while ago, done a lot of work in link state routing, and actually ISIS is her invention because she designed DECnet phase 5 rather, and ISIS is really just a copy of that. So you've already heard the acronym explained, and I'm a co-chair because Eric Nordmark is my other half. There's a couple terms that you may hear. Our bridge is a routing bridge. That's a device that implements the TRILL protocol. And our bridge campus is an assemblage of our bridges, links, and you can have bridges in there too. and it's bounded by end stations or routers. So an R-bridge campus is to R-bridges the same as a bridged LAN is to bridges. So what's the idea here? It's a very simple idea. I think all great ideas are very simple. You take native frames from end stations, you encapsulate them in a transport header with a hop count. You then route them using essentially normal routing techniques based on a fairly short tag indicating where they should go in terms of R-bridges. And then you decapsulate them and deliver them. So that's the idea. So we chose ISIS, so as part of the original design really, because of two reasons. Rather than OSPF, which you might think the IETF would prefer to use since the IETF designed OSPF. ISIS runs directly at layer 2, so you don't require any IP addresses. You would expect in the real world that our bridges would typically have an IP address for management or other reasons, but they don't require it. They can come up, find each other, start routing without there being any IP addresses or IP in the area. And it has a very flexible data format, so it's easy to add new kinds of fields you want and things like that. So it does lots of great things for you. Optimum point-to-point forwarding. I'll go through this real quick because I think you guys know all about this kind of stuff. So we have 3 bridges here. You run spanning tree. It works by turning off ports. You can't use that bottom link. Your frames do not follow optimal routes from B2 to B3. They got to go via B1. However, if you replace these with our bridges, then all the links are available, stuff follows the optimal route, and if you don't have something which specially requires configuration, like if you didn't have any particular VLANs things here, you could do this with no configuration effort or anything. Just upgrade your bridges to our bridges, and there you are. It does multipathing. This is a very simplified data center kind of diagram. If you have a bunch of paths disabled by spanning tree, you typically can only get one path between 2 points, but with our bridges you can easily get multiple paths. So that's actually optional, but I don't know of anybody implementing TRILL or our bridges that's not planning to provide that feature. So they're compatible with classic bridges. So if you have an existing bridge LAN, you can replace classic bridges with our bridges, and it's recommended you do that in such a way as to divide up your bridge LAN into small islands to reduce the size of your spanning trees. It'll basically reduce the problems from spanning tree, decrease settling time, and so forth. The forwarding tables at our bridges are the scale with the number of our bridges. Our bridges in the interior of our bridge campus don't need to learn end station addresses. Only the edge our bridges need to learn that. The TRILL protocol has an options feature, and one of the interesting things is because of the link state database, you can tell what options other R bridges support. So if you're thinking of using one, this feature hasn't been used very much so far, but if you were, then you would be able to tell whether the destination supported that feature before you actually composed or sent a frame there. And does optimize distribution of IP-derived multicast automatically is another optional feature, which I believe most every implementer of R bridges is planning to include. So there's lots of great features about bridges. You know, they're transparent, they got all this plug and play, they have support for virtual LANs, useful in lots of ways. They have frame priorities and actually sort of building on those priorities as kind of channel indicators. There's the data center bridging features, which let you sort of allocate bandwidth and prioritize things in various ways and decrease or eliminate loss of frames due to queue congestion. And they're currently under development for various virtualization support, edge virtual bridging stuff. But routers really have lots of great features too. I mean, just from the beginning there, they do great multipathing, find optimal paths, do rapid failover. They also have a safety of a TTL, which I think is pretty important. Many proofs or indications that some routing or forwarding system is guaranteed to work depend on this small assumption that the control plane is still operating. But in modern things are so complex, sometimes the control plane crashes, but the data plane keeps working. And typically the implementation of the TTL reduction and discard is in the fast path, so that can save you even if your control plane isn't working anymore in some particular box. And typically they support options. So our bridges are really a great combination of all these features from both bridges and routers. So you look at an R bridge campus, there's various different kinds of frames. There's the ISIS control frames, TRILL ISIS between the R bridges. There's the encapsulated data. There's still some layer 2 control frames sort of on the physical links, things supporting LLDP and stuff like that. One thing I should mention is that our bridges and TRILL are really built on top of 802.1q ports. So you can, for the most part, assume that the ports have all the features, and you can add various optional features like MACsec or whatever, link aggregation. All that stuff is kind of below TRILL, and you can do all those kinds of great things. And then there's native frames, which are the real end station traffic, which is essentially what you have if it's not one of the TRILL frames or one of the layer 2 control frames. So this is what a TRILL frame looks like between two R bridges. There could just be a wire between those R bridges, or there could be an arbitrary Ethernet cloud with 802.1d and 802.1q bridges and who knows what between them. So you have the original frame, you have the TRILL header, and you have a link transport header. And this shows an Ethernet link transport header, and it sort of shows a VLAN ID there, but you don't need that VLAN ID if it's point-to-point or anything. You only need that VLAN ID if there's like carrier Ethernet facilities in the way that restrict your VLAN or some other restrictions on VLANs. And you could use other kinds of links between two R bridges. It could be a PPP link or something like that, in which case you would have a different link transport header. So this data is encapsulated, as shown on the previous page, and that link header is really just to get it from the transport header, just to get it from one R bridge to the next R bridge. And it's unicast address for unicast frames and multicast address for multi-destination frames like broadcast or multicast frames. And the TRILL header, which I'll show in a second, specifies with the first R bridge the frame hit, where it was ingressed or encapsulated, then the last one where it's going to be egressed or decapsulated back to native form for delivery, except in case of multi-destination frames, in which case that same field actually indicates a distribution tree that the frame is sent on. So here's what this actual TRILL header looks like. Has a ether type if you're sending it on Ethernet. It's got the usual kinds of versions and hop count. It has the nicknames for the ingress and egress, and those are auto-configured. You don't have to worry about them at all. R bridges come up with those by themselves. And there's 1 bit which indicates whether it's a unicast or multi-destination frame. So TRILL data frames that have known unicast ultimate destinations are just routed really hop by hop with standard routing techniques. If they're multi-destination, they're forwarded on a distribution tree, as I said, by the ingress R bridge. That selects the distribution tree, and then the frame then follows that tree. In the case of multi-destination, there's a reverse path forwarding check, because multi-destination frames are potentially more dangerous. You can have forks in the distribution tree, and the frame could multiply, so you need more control over it. The distribution trees can be pruned, which basically just means that the tree is all still there, but it means you don't send the frame down some particular branch based on VLAN or multicast group or things like that, if you don't see any listeners down that branch. And it's important to keep in mind these distribution trees are campus-wide, shared, bidirectional trees. They're not restricted in any particular way, each of these distribution trees. TRILL defaults to 1, but you can configure your campus to calculate as many as you like. So in sort of the way things peer, things at the same level can peer, but if typically lower level things like bridges can't peer through higher level entities like routers, well, with R bridges you sort of have a new layer in the middle. Essentially looking downwards from a router, all the assemblage of R bridges and bridges looks transparent pretty much. But if you look upward from a bridge, the R bridges look like routers. They terminate the spanning tree, and otherwise they look like end stations from the point of view of bridges. So things can peer like as shown here, but not peer through higher level entities like that. So one way that TRILL actually treats VLANs somewhat differently from bridges is that it tries really hard to glue together all the end stations in a particular VLAN within a campus. So if you have two end stations that have access to an R bridge in the campus, and they're in the same VLAN, then they will be able to communicate with each other. So if you had a previous bridged LAN and you replace all the bridges with R bridges, a good thing to do. If they were previously VLAN islands, they will be glued together. And most customers think this is a good thing. But there is a feature which you can do to divide your campus into regions such that VLAN IDs are translated as they cross the inter-region boundary. If you desire, you can block traffic at that boundary so that a particular VLAN is actually divided into two different islands. And this really just affects the border R bridges. You just have to configure them. The R bridges in the interior of a region don't even know this is going on, and it has absolutely no effect on optimal paths, distribution trees, or anything else. The frames follow exactly the same path as they would before. It's just that as they actually transit a border between regions, you can provide for mapping of VLAN ID or priority or dropping of the frame. So, of course, a spanning tree protocol had a poem called Algorithm, which you can easily find on the internet if you do a search. And since Radio decided to design TRILL, she thought it clearly needed a new poem. So we have Algorithm version 2. And instead of her writing it, she had her son write it. So I'll leave it as an exercise to you to read this or find it by searching for Algorithm v2, I guess. Just a quick thing on data center bridging. Cisco coined the phrase data center Ethernet, and they initially used that to refer to 4 things really: priority-based flow control, which is known as per priority pause, enhanced transmission selection, congestion notification, and TRILL. And the first 3 of these are really what's referred to as data center bridging. And those 3 features, I don't want to go into detail, but they're really pretty much implementable in the queuing structure inside ports. And they can really be implemented inside the ports on most any kind of box. Be thought of initially as bridges because they're called data center bridging, but you can do them on R bridges. You can do it on, to some extent, on end stations, depending on which feature you're talking about, or routers or whatever. It depends a little bit. And so all these can really be implemented below TRILL in the ports on an R bridge and support that with one corner case related to congestion notification. So there is a minor extension to TRILL, and there's a draft explaining how to do that, where if you have a bridge in between 2 R bridges notices congestion and generates a congestion notification message, it'll generate it to the previous hop R bridge, which has to do a little bit of modification to the frame to actually get it back to the original source of that flow and try to restrain the flow to reduce congestion. So data center bridging is supported by R bridges. And actually, I usually attend the data center bridging sessions, so I'm in the next room when these guys are in the other room where the shortest path bridging work is going on. So just a little on the standardization status. As usual, it took like an absurdly long time to get to the current state of standardization for this. The first TRILL working group meeting was in March of 2005, and the working group was essentially through with the base protocol in December 2009. And the official announcement that the TRILL-based protocol spec was an approved IETF standard came out on March 15th. There'll be references, I guess, at the end of all this, which include a reference to the document which was approved. There have been ether types assigned. There's a block of multicast addresses assigned, of which it's a block of 16. Only 3 of them are currently in use for anything in TRILL, but the others are available for extensions. The network layer protocol ID. The only thing remaining is final approval of the ISIS code points and data structures. There has been, although those ISIS data points and code structures are in some sense pending, they've been stable for long enough that there's lots of implementations going on. There's been a publicly announced interop plug fest at the University of New Hampshire Interoperability Laboratory, which was at the beginning of August, and they're working on scheduling another one. And there's ongoing work in a lot of areas. Okay. So there's now some comparison section. So I'm going to start with some comparisons between TRILL and shortest path bridging. So it's possible that I've made some errors in this because I know more about TRILL than I know about the latest state of shortest path bridging. It's kind of a moving target. But I'll just go ahead here. So frame overhead, that's one question. Well, so these things add these additional headers and stuff like that. What's this all really cost? Well, if you assume you have point-to-point Ethernet links and you're doing multipathing and stuff like that, with TRILL takes 20 bytes extra stuff. You got outer MAC addresses and you got the TRILL header, which takes 8 bytes for the TRILL header. So my calculations show that SPBM in that case is 22 bytes. It's not a big difference, but it's a little bit more. And I have the arithmetic here as to what is added or subtracted for various tags and so on. Okay, that's in that case. What if you have like a complex multi-access links and, with multipathing and things are going on, and maybe you need the outer TRILL VLAN tag because there's complex VLAN filtering happening or something. So that bumps up the TRILL thing to 24 bytes. So as far as I know, SPBM just doesn't work on multi-access links. So it's hard to do the comparison in that case. I'm only talking about SPBM because there's actually 2 modes. Quite added complexity. SPB has these 2 different modes that, And in SPB-VM, the other mode, I just want to mention last time I saw this, it appeared that it consumed VLAN IDs at a cubic rate. Okay, so if you had n nodes and you wanted to handle real VLANs and do k-way multipathing, it took n times v times k distinct VLAN IDs, or like, a lot. So I don't think it scales very well. But anyway, routing computation. So that's something that might be important. So what does that take? So by the way, one great thing about spanning tree, spanning tree does have good features, is that as per the directions given to her by her supervisor over 25 years ago, Radio was told to come up with something that would let you hook Ethernet segments together that would scale as a constant. And something which seems absurd because that should, but in fact, spanning tree kind of scales as a constant, and unless you assume things are getting so big that like you have to make MAC addresses longer or something funny like that. So for practical purposes, the spanning tree scales as a constant. So TRILL uses the usual Dijkstra kind of stuff, and if you optimize that calculation for unicast, you get basically n log n is the calculation. By the way, for all these things with linked state, the storage requirements of the node approximately are order n. So I'm talking about the computation load. So, and you can do multipathing kind of automatically. In TRILL, you just keep track of the equal cost paths, which ports lead to equal cost paths, and it doesn't add much. In TRILL, if you're doing multi-destination multipathing, it's k times n times log n if you want to have k distribution trees. And there isn't really a reason to have a whole bunch of distribution trees. People tend to get confused about that. They didn't say, but don't you need lots of trees? Isn't there congestion at the root of the tree and stuff? Well, these are bidirectional trees. You don't send stuff to the root and have it redistribute or anything like that. Each arbridge just injects it into the tree where it is on all the branches leading out of that arbridge. And so in this sort of the general case, the result is that a broadcast frame, for example, sort of goes to every node. So it means it crosses every link exactly once. It means there's equal load everywhere in the tree. That's a simplification, and there's some second order effects. So there is a feature where you can have more trees. You can even have multiple trees rooted at the same arbridge if you want to use different equal cost path trees out of that one because one particular node is a very large source or sink for multi-destination traffic. So what's the story on shortest path bridging? Well, I understand they're working on improving this, but for unicast and multicast, they're really kind of unified, so that's a good thing. But the cost is really k n squared log n, where you're doing k-way multipathing. And k is currently, at least in the spec draft, limited to 16. So, it's really not much multipathing. And it's very, so they're talking about a 1,000 node network. So that means every, well, maybe you can simplify it. They have found some optimizations, but at least some boxes are doing 3 orders of magnitude more computation than TRILL is to handle 1,000 nodes. Maybe that has some significance. So I'd also like to just do a brief comparison of the way these protocols have evolved. Well, what are we going to do relative to the slide? Are they going to give their point, or are they just going to answer me?
I'm going to go to some questions because we're running a little bit tight.
So am I going to get to present this?
We can actually cut off the slides now. We can get to
No. Sorry, I'll go through these really quickly. I've been told I'm sorry I wasn't notified or anything. So anyway, just real quick, the history. Radia invented the spanning tree, and she invented this whole concept of the TRILL concept of transparent routing. So she gave a tutorial at 802. I know because I arranged it, and in fact they require more than one speaker, so we actually both spoke. I spoke about 2% of the time, and Radia spoke about 98% of the time. So 802 said, go away. She gave a BOF at IETF. IETF thought it was good. They formed a working group. I say I'm going fast. So what happened in TRILL? So her idea was accepted. The basic idea is very simple. I gave it before. Shortest path transparent frame routing, using real routing, using ISIS and encapsulation with a hop count. So early on, additional data plane learning was added, the VLAN support was all added, and in the future I suspect that something like ISID support will be added, but I don't want to speculate too much about things that haven't actually happened. It was found after about 18 months ago that there was a need to add some MTU robustness, and that's been added. So TRILL actually has facilities so you can like track all the MTUs on your links. You can report them in the link state. You can do traffic engineering, so you can select routes that support jumbo frames, all kinds of great stuff. And in the future, more stuff will be added, I'm sure. So last slide. What happened in the evolution of SPB? So radio ideas were rejected. Basically, I was there. People said there isn't really a problem. I mean, who needs more than 65 trees you have with multiple spanning tree? And if you do, maybe you can do spanning tree per VLAN. You know, TRILL is pretty terrible idea. Spanning tree is great. Routing's terrible. Hop counts are bad. I hear people say that. But the IETF formed a working group. Hey, it's a challenge, you know? So they decide, well, actually, maybe there really is a problem. So they spin up 802.1AQ, and the initial idea was perfectly clear. I mean, it's not in the charter, but you can see the initial stuff. Initially, 802.1AQ was going to be based on a huge number of spanning trees, because spanning trees are good and routing is bad. But, well, you know, and it's, by the way, when I say they say, this is individuals. This is not the official word of 802.1. It's not, they're more polite than that. But actually that turned out to be a problem. So they decided actually spanning tree really doesn't hack it, even though that was the initial idea for 802.1AQ. So we'll start cribbing more from TRILL. So they start using ISIS and nicknames. They call them SP source IDs. But they don't really do routing. They just use that to configure this bridging stuff. And they still say, you know, TRILL's not so good. Some individuals, and not the individuals present here, I have to admit, who are excellent people. The latest thing is they've figured out that 16-way multipathing just doesn't hack it. They can't multipath enough. You know, they're trying to figure out ways to make it multipath better. The link agreement protocol they have, which is a critical part of it they didn't mention, you know, hasn't really been tried much. It's very complicated. They're trying to find out some way to fix that or you know, shoehorn TTLs into it, even though most people in 802.1 that I've talked to believe that TTLs are still bad and that, you know, they're not really effective and stuff. But you know, they're really kind of like, they got to figure out some way to catch up to TRILL. So that's my view.
Thank you very much, Donald. Appreciate that. Yeah. So, just before we, just because we're short on time, I just want to give you guys an opportunity to respond to some of the last points that Donald made before I ask a few few leading questions.
Sure. Well, I mean, the one of the points that comes up fairly frequently is this whole business of computational complexity, and when we first started working on 802.1AQ, yeah, it was something that we were concerned about, and then we actually tried implementing it. We sat down, we wrote code, we optimized it on some of these 2 and 4 gigahertz multi-core processors that are making their way into the kinds of switches that we have. And lo and behold, we were able to do 400 or 500 node networks with tens of thousands of services, and they were completing in 10, 20 millisecond calculation times or less. So there are, it's very important when you throw up these order of calculation comparisons that you understand what those n's are and what those k's are and exactly what kind of computational power you're working with. I mean, if we were always worried about using our CPUs to do anything, we wouldn't waste CPU on the user interfaces on these things, and what a horrible waste that would be. So, you know, if you're really concerned about it, go look at the IEEE website. There's a series of presentations that were made on the computational complexity. We brought all kinds of examples. We ran it on, I don't know how many different processors. And so for the scales of networks that we're interested in, it really did not concern us after we actually implemented it. The other thing that I would bring up is that the computations are producing useful state. If you're going to do the computation and you're going to produce multicast state on those kinds of scales, every single one of those forwarding entries is saving you bandwidth somewhere. If you don't want to do it, the option is there to turn off the multicast replication at the transit points and do head-end replication just as you do with VPLS. And in that case, by the way, the computation is less than TRILL. So that's my point about computation. I really hope we can move on from that to something more productive, because there are much bigger issues at stake here. This is really, in my book, an issue about the Ethernet frame, the Ethernet work, all of the work that's gone on over the last 30 years on Ethernet. Do we want to continue that work? Do we want to make some small changes to it where necessary? If there are some changes required, IEEE is perfectly willing to do that. Yes, you have to sit down and you have to be willing to work carefully and politely and quietly at the IEEE, but it's possible to do it. So that's the first thing. Do we want to change? Do we want to create a brand new encapsulation? Do you want a new encapsulation in your network? Do you want brand new OANM? That doesn't exist. Their slides are way better than our existing implementations, I'll grant you that, although I haven't even seen the slides, but I'm sure they're better. So we have years and years and years of Ethernet OANM. You're all probably using it. Do you want to continue using it, or do you want something brand new? I don't want something brand new. I want to build on it. I want to solve more interesting problems than OANM. Look at what's going on in MPLS. We've got brand new OANM. It's still ongoing. It's a very, very lengthy exercise to introduce. There are thousands and thousands of man-years involved. Sure, there are lots of other small, minor differences and some not so minor differences between what 802.1EQ and shortest path bridging are doing. But there are big, overarching considerations here with respect to continuing our work on Ethernet, preserving our work on Ethernet, and moving it forward. The IEEE is perfectly willing to do that. There are probably lots of other points. I don't know if one of you guys want to step in.
Actually, let me roll to one quick question. Donald, can you speak to OANM and how TRILL handles that?
Hello? Hello?
Should be, yeah.
Can you hear me out there? Okay, I can't. Now it's sorry. OANM. It's a great thing. You should have OANM. I agree with that. And there are OAM drafts that haven't been posted that are in development. I mean, what do you do with ISIS for OAM? You run BFD typically, right? You know, there's a draft on BFD for TRILL. BFD is a well-developed protocol, and there's a draft on other facilities. And these are new drafts. That's absolutely correct. But you know, it doesn't seem completely like rocket science to me. So. That's what I have to say about OAM.
Okay, thanks. I had a couple other, I'll just bring up kind of list here, a couple leading questions. Question was raised about intellectual property. So what's the status of whether or not there are any rights or any limitations on intellectual property for the TRILL implementation?
Sure. The original idea was patented by Sun Microsystems, and Oracle, because of the acquisition, now owns that. And that patent, and actually all other IPR that Sun owned, is licensed royalty-free worldwide in perpetuity, as long as your implementation conforms to the IETF standard.
And similarly for SPB, are there any royalty considerations?
Not that I'm aware of. Obviously, I'm not a lawyer. I'm not allowed to speak on behalf of the company that I work for. And I suspect that's true of every one of the panelists here. Making legal statements about specific products on specific companies is it's outside of the realm of my pay grade.
Sure.
All I wanted to say was that last time I checked, there were 5 different IPR filings with the IEEE related to 802.1AQ by 5 different companies, and I believe they were all reasonable, non-discriminatory royalty-bearing disclosures.
Standard practice in the standards bodies, but again, I'm
standard practice in the IEEE, not standard practice in the IETF, which is much more allergic to patents than the IEEE.
So I'm not really sure what the problem is. Every single routing protocol in the world that we all use day to day are all wrapped up in IPR. What's the problem? Honestly, I mean, MPLS, tons of patents. VPLS, tons of patents. IPVPNs, tons of patents by all companies, right? They're all going to be wrapped up. The users don't have to worry about them. The lawyers will take care of it. It's just like everything. Ethernet, the original Ethernet's still wrapped up. Spanning tree still has patents related to it. There's no big deal.
There's those spanning tree patents that I'm aware of.
I'm going to roll the next question. Question about TTL. So you guys are handling TTL differently. What's the take right now on SPB and the necessity for TTL to be handled?
you go.
So TTL is this kind of interesting topic. For years, because it basically means you got to add a completely new header encapsulation. We're not against the TTL. It's just the point is that when we were working through the standard itself, we were more worried about making sure that, you know, one person put it really nicely. A TTL is not a solution to looping. A TTL is dimensioning how big you want your crater to be when a loop forms, right? So solve the damn problem of looping first. Make sure loops can't occur. And if you want to put a TTL at the end when you're done as like an airbag, fine. It's a nice little thing to have at the end. But let's solve the actual looping issue in the beginning. So there's a lot of work that goes in, that's in the actual spec to guarantee there's no looping inside of the network, basically protecting against paths not being used for forwarding that shouldn't be used. Right?
And the TRILL take on TTL?
It's routing. You know how IP routing works. You know how ISIS routing works. The idea is very simple. You encapsulate the native frame in a header with a hop count, and you route it with a TTL, like routing, and then you decapsulate and deliver the native frame. TTLs are great.
Except for multicast, where you also do a reverse path forwarding check.
That's correct. And I was simplifying by only speaking about unicast, and then I explained in my talk why multicast is more dangerous and requires greater care. But in both cases, there's a TTL, which protects you from such disasters as a crash.
So for the more dangerous stuff, you need a reverse path forwarding check, which is built into shortest path bridging and is a byproduct of the symmetry of the routing. Exactly. One of the things that we've done is we've made sure that the routing is symmetric and congruent, precisely so that we can use this extremely strong, which Donald just described, reverse path forwarding check, not only for unicast and multicast. You actually need a simultaneous loop to form in both directions to break a reverse path forwarding check.
Thank you. Next question was actually regarding symmetry. So is symmetry really necessary?
Well, so symmetry is necessary for a reverse path forwarding check, but it's also something which many people find desirable. I will grant that there are lots of cases where symmetry and congruence are not necessarily something that is essential. However, there are a lot of cases where knowing exactly where your packets are going, being able to predict with an offline tool exactly where your packets are going to go, and looking at your network and seeing exactly, I mean, Srikanth gave a little demonstration where he showed the multicast tree looks exactly like your offline tool predicts. Your network does exactly what is supposed to be happening in your offline tool, and if there's ever a difference, there's a problem. The other thing is you can go to the core of the network and stick a probe in the network and look at a packet. You can see the source that it came from, the destination that it's going to, the service it's on, and the route that it's on, and it won't change. And that's a useful thing.
And the symmetry view within TRILL?
You can tell what path some frame is going to follow. I mean, it won't change unless in TRILL either, unless there's some topology.
Well, the hashing will change it.
What?
The hashing will change it.
What hashing?
If there's no symmetry.
The paths are not guaranteed to be symmetric in TRILL. It's ISIS routing. It's just IP paths are not guaranteed symmetric. It uses ISIS in its way somewhat like IP. It's not actually routing on IP addresses because MAC addresses are a flat space and they're not hierarchical. But it's somehow the internet gets along without all internet paths being symmetric and similar and so forth.
Well, so I'm not against asymmetry. I'm saying that there's a case for both. One of the analogies that I like to use is that there's this shotgun-based forwarding, which is spreading the traffic on multiple paths with ECMP, which results in asymmetry. And then there's the use of more careful symmetric routing to guarantee the symmetry and congruence, and we call one the shotgun and one the rifle. And when you go hunting, it's nice to be armed as well as you possibly can be. I want a machine gun as well.
And so there's a lot of workarounds we've done in MPLS. I mean, we all have seen the way we forward and do ECMP and MPLS. There's a lot of congruence in what we've done in the IEEE as well for this. Again, most of the people working on this came from an MPLS development background. So as far as symmetry goes, is it required? No, but we look at it as a nice way of guaranteeing loop-free environment. And there's actually quite a bit of work going in saying, well, if you want to do a shotgun effect, you can ease up those restraints and do it if you'd like.
Okay. Thank you. So we're running a little time. I'm just going to ask one more question here. It's regarding scale. You'd mentioned 16 million with ISIDs, and you'd mentioned NICs, which I believe go to 64,000. What are the scaling, some of the scaling limitations as far as number of paths go, number of unique? I'm going to start with on the TRILL side.
The routing. I spoke about the routing computations and stuff like that. I mean, so I don't know that there's that much difference actually in the number of switch kind of things, other than the higher computation requirements. In terms of number of the real question I think you're asking is related to VLANs and ISIDs.
Number of VLANs and services.
So currently TRILL is VLAN based, and it's quite clear. But I believe that TRILL is easily extended to be able to handle equivalent of ISIDs, and but that would be something which has not yet happened, so that's all I can
Are we
really
going to
say.
invent Mac in Mac again?
What?
Are you going to invent Mac in Mac again with a new ISID?
No, not necessarily. How about the same ISID? I don't know.
And from the SPB side?
Yeah, sorry.
I'll answer to that. ISITs as a number space 2 per 24, have we tested, what's the scalings we tested in live networks and test topologies in our labs? We've been able to drop 100,000 multicast trees on our switches in the core links, and as a comparison, that's one multicast tree for everybody in a decent sized city and their family members. I mean, that's, when you're not even touching IEEE on multicast scaling, and this isn't just lab numbers. We could put them in live networks, and they are running in live networks right now.
Thank you. Let me give just 2 minutes for closing remarks. If you gentlemen want to select someone to give a 2-minute closing.
I guess I get elected to do the summary. So I'll just reiterate what's already been said in a lot of cases. I mean, I personally, as an individual, don't see what the big debate is about this. The Ethernet has been owned by IEEE for many years. There's a lot of changes that are going on in IEEE beyond even what we're talking about with SPB. We're doing a lot of work on new access links and technologies with VDP and even all the standards that Don put up there a second ago of ETS, PFC, and all those other things for data center Ethernet. Those are all being done in the IEEE, right? Every single one of the meetings that we go to, we sit there in a room with the data center guys and us, all working through the standards. And we've already done cross changes back and forth with each other. So as these things continue to change, you're going to have to constantly upgrade and look at the protocols. And the one thing that is kind of missing out of this debate is the fact that we took the basis, because the IEEE has been working on Ethernet for over 30 years, we had to make sure that what we were doing would work with 30 years of Ethernet, so in place. So not to force you to upgrade and rip and replace networks, because obviously that's not going to happen. Right? So the intent is basically from a migration path, you simply would just turn on another VLAN that's running SPB and turn on another set of VLANs that's running SPB. And from a multipathing basis, we can go from 2, 16, and even at the last IEEE meeting, there was an option put in there for an infinite number of ECMP paths if there was an infinite number of paths available. And the reason why is because we made it very modular. You can plug in any multipathing algorithm, and it's basically just a little TLV in there that sets which one you're doing. So as far as extensibility, scale, I mean, as we've been looking at this thing, we look at pretty much any environment you can imagine wanting to deploy Ethernet in a large scale that support IP. And I think it shows from the scale we've seen actually in live deployments already.
Thank you. And Donald from the TRILL side?
Hi, so I guess it's really true. Certainly IEEE 802.1 has been essentially blinded by radio's brilliance in the invention of STP for over 25 years, and was really unable to see anything outside of that until she came up with this idea. And they're madly busy, trying to leverage as much of it as they can without really taking the whole of her genius in inventing TRILL.
Great. Well, thank you very much, folks. As I mentioned at the end of the slides that are online, there are some references that were provided by both groups here. So just to recap what we have going on for you this evening, first of all, please, if you have a moment, sometime between the break or between the evening events, hit that survey. It's good for you, good for us. We have the vendor collaboration room that begins right after the break here, and that is through the elevators and to the right. We have the beer and gear at 6 p.m. in the exhibit hall, which is through the elevators, and I think to the left you'll find it through the, sorry, that direction. Thank you very much, Mike. And this evening at 8:30 p.m. we have the evening social at Shout. So thank you Telex and Cisco and NTT America for sponsoring that. That should be it for this afternoon. Thank you very much.